These are examples for section 4.5, isosceles, equilateral, and right triangles. Example 1. Prove the Isosceles Triangle Theorem. This is also known as the Base Angles Theorem for triangles. We have triangle XYZ, and we're given that XY is congruent to XZ. They've already marked these. That's given to us. We're also given that XB bisects angle YXZ. Again, that was given to us. Since XZ bisects angle YXZ, angles 1 and 2 are congruent. And the reason why we know they're congruent is because by the definition of angle bisector, this bisector XB created these two congruent angles. So angle 1 and 2 are congruent by the definition of angle bisector. Now, from this point on, we're trying to show that angle Y and angle Z in triangle XYZ are both congruent. At this point, notice that we've created two triangles, XBZ and XBY. And if we can show that the two triangles are congruent, then at that point, we can go on and show by CPCTC that angle Y and angle Z in each of these two triangles are corresponding and congruent. So that's our plan. So we try to show that the two triangles are congruent now. Notice we've got two pairs of corresponding sides in the two triangles that are congruent, and we have two corresponding angles in the two triangles that are congruent. So we have side and we have an angle, side, angle. So we'll either use SAS, AAS, ASA. Notice we have XB in triangle XBY and XB and XBZ, triangle XBZ, both being shared and are congruent. So XB is congruent to XB in the other triangle. This is the reflexive property of congruence. And if you'll notice now, we've got enough to use one of the triangle congruence postulates: side, angle, side. Side, angle, side. So by the side, angle, side congruence postulate, we can now state that triangle XBY is congruent to triangle XBZ. Now, since these two triangles are congruent, all their corresponding parts must be congruent. Angle Y and angle Z are congruent because angle Y in triangle XBY corresponds to angle Z in triangle XBZ. So we can now say that angle Y is congruent to angle Z because corresponding parts of congruent triangles are congruent. We already showed that the two triangles were congruent. We've just proved the Isosceles Triangle Theorem, or the Base Angles Theorem. Example 2. Complete the paragraph proof below. Then, based on the proof, find the value of x. Here we have triangle ABC, and we've got a segment BD going through. We've got a 54-degree angle here at angle A. We've got x degrees right here. That's what we're looking for ultimately. Notice that we've got AB is congruent to BC. We've also got angle ABD is congruent to angle CBD. This is all given to us in our diagram. This will be the first time we have written a paragraph proof with lots of help. So let's complete this one. Remember that all the components in a two-column proof must be evident somewhere in the paragraph proof also. So we start, given that side AB is congruent to side CB. Also given that angle AB, side AB is congruent to CB, that tells us that angle A must be congruent to angle C because of the Isosceles Triangle Theorem. So since these two sides are congruent, the angles opposite them must be congruent by the Isosceles Triangle Theorem. New sentence: since angle A is congruent to angle C that we just showed, the measure of angle A is equal to the measure of angle C. If two angles are congruent, then their measures are equal. That's the definition of congruent angles. So, since angle A is congruent to angle C, the measure of angle A is equal to the measure of angle C by the definition of congruent angles. New sentence. So, since the measure of angle A over here is 54 degrees, that's what we're given, we can now say the measure of angle C is 54 degrees, since they're equal in measure. Next, BD bisects angle ABC by the definition of angle bisector. BD, because these two angles are congruent here and here, this must be the angle bisector of angle ABC. This is where we get the definition of angle bisector. Because it is given that angle ABD is congruent to angle CBD. Like we said, these two are congruent. New sentence. Since segment BD is an angle bisector, as we just mentioned earlier, AC and BD must be perpendicular, and also AD must be congruent to CD, both of these by the Isosceles Bisector Theorem. New sentence. Then by the definition of perpendicular lines, since these are perpendicular, angle ADB and angle CDB are right angles. Notice what we're doing is we're building all the measurements in this triangle here so that we can find the measure of angle X, or the measure of the angle that has this X. We've got 54 degrees. Now we're about to get 90 degrees. The definition of right triangle, excuse me, the definition of right angle tells us that the measure of angle CDB is 90 degrees. So since the two segments were perpendicular, by the definition of right angle, we now know that one of those or both of the angles are 90 degrees. So now we know this is for sure 90 degrees. Now we've got what we need if we use the triangle angle sum theorem. So by the triangle angle sum theorem, the measure of angle DBC, which is X, plus the measure of angle C, which is 54 degrees, plus the measure of angle BDC, which is 90 degrees, is equal to 180 degrees. Now we can locate or find the measure of X, or the value of X. So X plus 54 plus 90 gives us X, combining like terms, plus 144 equals 180. Subtract 144 from both sides, and X is 36 degrees. So X is 36 here, and this was the paragraph proof to show that this angle was a certain measure that we could find, and we found it was 36. Example 3. Find the values of X and Y. Then find the measure of angle P and the measure of angle M. In this diagram, we have two triangles actually we have three triangles, two next to each other, adjacent to each other. Notice that the two triangles, we've got triangle MON right here, and we also have triangle NOP right here, both of which are isosceles triangles. This is isosceles because these two sides are congruent. This one's isosceles because these two sides are congruent. The fact that they both share the same side is coincidence, but we can probably use that to our advantage. The angle ONP is 50 degrees here. We're also given that the measure of angle NOP is 2y plus 64, and the measure of angle NMO, or angle M, is 45 minus x over 4 degrees. So, if you'll take a look at the two triangles, the triangle MON, we don't quite have enough information to use triangle angle sum here. We've got this angle right here. We don't have this one yet, and we don't have this one yet. So we move over to this triangle, triangle NOP, and notice that we've got enough, or we will have enough. Notice angle ONP is 50. We've got this one right here, 2y plus 64, and this angle right here is the only one we need to find. Notice, again, since this is isosceles triangle, that by the Isosceles Triangle Theorem, since these two sides, NO and NP, are congruent, the angles opposite them must be congruent. So let's write that. Angle P is congruent to angle NOP. And by the definition of congruent angles, the measure of angle P is equal to the measure of angle NOP. Well, the angle of these measures here, since this angle NOP is 2y plus 64, it's the same as the measure of angle P. That means angle P is also 2y plus 64. So now, if we use the triangle angle sum theorem, we can add all three of these angles up and solve for y. So by the triangle angle sum theorem, we can now say the measure of angle O, which is 2y plus 64 degrees, plus the measure of angle P, which is also 2y plus 64 degrees, plus the measure of angle ONP, which is 50 degrees, equals 180 degrees. Next, we combine like terms on the left side of the equation, and we get 4y plus the 64 plus 64 is 128. 128 plus 50 is 178, equals 180. Then solving for y, subtracting 178 from both sides, we get 4y equals 2. At this point, we need to divide both sides by 4 to get rid of the 4, so we'll have y by itself. When that happens, we get 2/4, or reduced. That gives us 1/2. So y is 1/2. Now that we have y, we can find the measure of angle P. So the measure of angle P was 2y plus 64 degrees. Substituting in y, we have 2 times 1/2 plus 64 degrees. 2 times 1/2, those divide out, and we get 1. 1 times 1 is 1, plus 64 degrees. So the measure of angle P is 65 degrees. Now that we found y, we can now locate or figure out the measure of this angle right here, so that we can do something very similar to what we just got through doing with triangle ONP, but with triangle MON. These are the two congruent sides. This is the vertex angle. This is one of the base angles. Since these are congruent, these two angles have to be congruent by the Isosceles Triangle Theorem. So by the Isosceles Triangle Theorem, once again, this time with this triangle, angle M is congruent to angle MNO, or the measure of angle M is equal to the measure of angle MNO by definition of congruent angles. So, since those are equal, we can say that since angle M is 45 minus x over 4, angle MNO has to also be the measure 45 minus x over 4 degrees. Now we have everything we need, almost. We have to find this angle right here, this vertex angle. Notice that this line or segment and this segment create a linear pair, and we already know what the measure of this angle is. Angle P was 65 degrees, so this one has to be 65 degrees. So since this angle right here is 65 degrees, this angle right here can be found by using the linear pair postulate. So by the linear pair postulate, we have the measure of angle M, the measure of angle MON plus the measure of angle NOP equals 180 degrees, linear pair postulate. The measure of angle MON is what we're looking for, plus the measure of angle NOP, which is 65 degrees, we found it earlier, equals 180 degrees. Subtracting 65 from both sides, we get the measure of angle MON equals to 115 degrees. So now we can place 115 degrees here and get a visual. This vertex angle is 115 degrees. This angle right here is 45 minus x over 4 degrees, and this angle right here is 45 minus x over 4 degrees. So now we have enough to use the triangle angle sum theorem once again, except this time to find the value of x. So by a triangle angle sum theorem, we can now say the measure of angle M, which is 45 minus x over 4 degrees, plus the measure of angle MNO, which is also 45 minus x over 4 degrees, plus the vertex angle here, angle MON, which is 115 degrees, equals 180 degrees. Combining like terms here, 45 plus 45 is 90, minus x over 4 minus x over 4 is minus 2x over 4 plus 115 equals 180. We can still combine these two numerals or like terms, and 90 plus 115 is 205. So 205 minus, and then 2x over 4, 2/4 reduces to 1/2, or just x over 2, equals 180. Now, we need to get rid of 205, and then after that get rid of the dividing by 2. So first of all, we subtract 205 from both sides. When we subtract 205 from the left side, we're left with negative x over 2. When we subtract 205 from the right side, we actually get a negative, and that's negative 25. To get rid of the negative and the 2, we multiply both sides by 2, or 2 over 1. Negative 2. Negative times negative is positive, and the 2's divide out, we get positive x. That's what we were looking for. Negative 25 times negative 2 is positive 50. So x is 50. Finally, we were asked to find the measure of angle M. The measure of angle M was 45 minus x over 4. So the measure of angle M was 45 minus x over 4 degrees. So the measure of angle M is 45 minus x, which is 50 over 4 degrees. So the measure of angle M is 45 minus, this reduces by 2, and we get 25/2 degrees. the measure of angle M is equal to 45 minus 25 halves. If you divide 25 by 2, you get 12.5 or 12 and a half. 45 minus 12 and a half degrees. Measure of angle M, when you go ahead and subtract those, you get 32.5 degrees, or 32 and a half degrees. We found the measure of angle M, the measure of angle P, we found X, and we found Y. Example 4. In example 4, we're asked to prove a situation where we're going to end up having to use a Triangle Congruence Theorem, but we're not going to be able to use sides and angles like we always traditionally have. Let's take note of what's going on here. And we're given quite a bit of information. We're given BE, segment BE bisects segment AD. So look at it closely, make sure that we look at this correctly. BE, this right here, bisects is doing the bisecting. It's bisecting AD. That means AD is being cut up into two congruent parts, with C as its midpoint. So this was given to us. And also AB, side AB, is congruent to side DE. So we mark those on our drawing. C was the midpoint, and C being the midpoint caused AC to be congruent to DC. And that's by the definition of midpoint. If a segment has a midpoint, then the midpoint creates two congruent segments, AC and DC. Then we go back to our given and write down, let's use the perpendicular statements here. AB is perpendicular to BC. So AB and BC are perpendicular. And also they give us that DE is perpendicular to EC. DE and EC perpendicular. This was given to us. Now from this point, we can actually state that since these two segments are perpendicular and these two segments are perpendicular, they create right angles. So angle ABC and angle DEC are right angles. If two line segments, in this case 4, if two segments are are perpendicular, then they create right angles. That's the definition of perpendicular lines. And we've already marked our drawing with right angle symbols. Now we know these are two right angles, but we haven't officially stated that they're congruent. So if these are right angles, are they congruent? Yes, they are. Angle ABC is congruent to angle DEC. Why? Because there's a theorem that states that all right angles are congruent. So you can write that, or you can write it by its title, Right Angles Congruence Theorem. All right angles are congruent. Now we have more of what we need. This is all the given information. We've used every bit of it. You take a look at the two triangles and notice that we've got two sides, but we don't have an angle in between the two sides. And AAS and ASA both require two angles. We only have one angle. Now we could go ahead and find BCA and ECD using vertical angles, but I'm going to skip that step and show you another way that's a little faster. So we can't use those. We can't use SAS because we don't have an angle included between the two marked sides, here and here. So we can't use that, and of course we can't use SSS because there are no angles at all. So what do? Well, the HL Congruence Theorem states that if the hypotenuses of two triangles and the corresponding legs of two triangles are congruent, then those two triangles must be congruent right triangles. So you've got these are both right triangles, first of all. They have to be right triangles. And then you've got the hypotenuse of one and the hypotenuse of the other marked and congruent. And you've got one of the legs in one and its corresponding leg in the other. That's all that's required for us to use HL. So by the HL, or hypotenuse leg congruence theorem, we can now state that triangle ABC is congruent to triangle DEF, or DEC. Caution, there is no such thing as ASS. There's no such thing as SAA. And there's no such thing for congruent triangles as AAA. These do not exist. You can't use them to prove triangles are congruent at all. Example 5. For which values of x and y are the triangles given congruent by the HL Congruence Theorem? Here we have two right triangles, and we want to know what values do x and y have to be in this situation. They're all over the place. So that these two triangles would be congruent to each other. All their sides and angles all congruent correspondingly. So we need to force these two triangles to be congruent and see what values of x and y need to be there so that that can happen. So using the HL Congruence Theorem, we notice the hypotenuse in each triangle. These would have to be congruent to each other. That would mean these measurements would have to be equal. So we set this expression equal to that one because they're both of them are the hypotenuses of both triangles. So we have 3x plus y equals, we set it equal to 3x plus 2, the two hypotenuses. And we're going to need another equation because in this equation we've got x and y. We can't solve for one of the variables. So we come over and we look and we notice we have a leg, the longer leg in this one and the longer leg in this one. If these were to be congruent, then we would be using HL, the hypotenuse and the leg. So this leg right here has to be congruent to this one if we were to use it. That means this measure has to be equal to that one. So we set this one equal to that one. So 5x minus 3, set it equal to the leg in the other one, 2x minus y. And we have two equations with two unknowns, so we have a system of equations. Two equations with two unknowns. From Algebra 1, you learned how to solve these. This one degenerates a little bit, so it's not going to take as much work, because I want you to notice in this first equation, here's our equation 1, here's equation 2. In our first equation, when we go to solve and we subtract at 3x from both sides, look what happens. When we subtract 3x from both sides, those cancel or divide out, those not divide out, they subtract out, these subtract out, and we're left with y here, and we're left with 2 over here. So we just got lucky on that one and got y equals 2. We already found the y value, so y is 2. But then, to find x, we're going to have to come over to the other equation. We're going to have to use the y that we found, and we're going to have to substitute it in here. So we substitute equation 1, y equal 2, into equation 2. So we take this and rewrite it. 5x minus 3 equals 2x minus y, which is 2. And then solve for x. X is the only variable left. So this would be subtracting 2x from both sides. We get 3x minus 3 equals negative 2. Don't forget the negative. Then when we add 3 to both sides, we get 3x equal negative 2 plus 3 is positive 1. Then dividing both sides by 3, so we can get rid of this 3 here, we get x is 1/3. So for these two triangles to be congruent, and using HL Congruence Theorem, x would have to be 1/3 here, 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 and here, and y would have to be 2 here and here.